Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and look further into probability and look at average values again. And this time go over example 1 and of the example series. Basically solve this example which says find the mean. Again, mean just another way of saying average of the exponential distribution or exponential probability density function, just to be exact. Same thing, the exponential distribution, it's often used interchangeably with probability density function. Of the function determined in my earlier video, probability example 2, so make sure to watch that in the links below, and that's this one right here. Yeah, this is a function that I went over in that video. So f of t is equal to 0 if t is less than 0, and equals c times e to the power of negative ct if t is greater than or equal to 0, and again where c is just a constant. So in solving this, recall from my last video on average values that the average value is it's the same thing as saying mean. So it's the mean, and it's usually written as mu, the Greek letter mu, and it's equal to, like I showed in my earlier video, so it's the integral from negative infinity to infinity of t times f of t dt. In this case we're dealing with function of f as a function of t instead of x, so it doesn't matter, just a different variable. Yes, so now in our case, our probability density function here, f of t, is broken up into two parts here. So we could break this mean formula into two parts, or this integral into two parts. So we can go from negative infinity all the way to 0, because this one is just less than 0, and this is going to be of t times f of t dt, and then plus the integral from, well, 0, anything greater than 0, so up to infinity, of t f of t dt. And now when we plug in our f of t's, what we end up getting is negative infinity to 0. When you plug this in, you just get, well, integral of 0. And then plus this one, 0 to infinity of t f of t. I should plug this one. This one is c times e negative c t dt. And again, so integral of 0, there's no area under this curve, is just 0, so that goes to 0. So we're just left with this part right here. So the average value mu, or the mean, is equal to the integral from 0 to infinity of t, write this bit neater, t times c e negative c dt. Yeah, but over here it's a infinite interval right here, so we can't just solve it directly like that. So, but instead we could write this as a limit. So I'll limit as x. I'll use x, the variable. Just we have t there. So as x approaches infinity, and then replace the infinity there. So from 0 to x, t c e negative c dt. So now we're going to deal with this integral right here, as opposed to dealing with the infinity, and then later we'll take the limit. So, yeah, we could solve this integral by using parts, integration by parts, and I'll show you why. So recall integration by parts. So in my earlier video, I went over this, and you could also see this more in detail in the video link below and the proof for it. So what we have, if we recall, if you have a function like u dv, this would just equal to uv minus, and then this is v du, so we just interchange. And the idea is we would write it like this so that we could simplify this, because this is like two functions multiplying by each other. And if we choose t as u, the derivative to get du is, well, that just cancels, so it goes to 1. So the idea is to make a simpler integral, because right now it's not straightforward solving that. So we go let u equals to t, so that du is just, well, 1, and then just write it as differential, so dt. And then dv is the rest of the part of this equation, so c e power of negative ct, c e negative ct, and then this is dt. And the reason we have this one you could take the integral pretty easily and see what happens here when you take the integral of e to the negative ct. That's itself is a constant. It's added like that. The integral of exponential function is itself, but then we have to divide by this negative c constant, because when you take the derivative, you're using chain rule, and then that cancels out. So we have this. As you can see, the c's cancel, so this just equals to negative e power of negative ct. So now what we can do is put this together. What we end up getting is, I'll write this out just by the integral by itself without the limit. So 0 to x of t e negative ct. Oh, there's another c right here. There's a c like that. So yeah, tc e negative ct dt equals 2u, which is t, times it by d times it by v. Yeah, so v is negative e negative ct. Then we subtract. So what we subtracted by is the integral from 0 to x, and then this one is we evaluate this from 0 to x as well, because we're doing, this is a definite integral, this one is just indefinite. You could just put in the intervals like that. So this is from 0 to x, and then now we write v, which is negative e negative ct. So we could, there's a negative one, so this just becomes positive. This becomes e negative ct, and then du, which is dt, like that. Yeah, so now evaluating this, we get, plug in the x, and there's a negative one like that. So this is going to be negative x e to the negative cx, and then plug in 0, so minus, and again, so this is going to be minus, and then because there's a minus already there, we just put a plus to make it easier. So minus becomes a plus, the t becomes 0, and then this is e to the, 0. I'll just erase the negative. It's 0. So that just goes to 0. This goes to 1, then it goes to 0. Goes to 0. And then this part right here, plus, and then evaluate this integral, we get e to the negative c. Yes, the integral of e to the negative ct is exponential function is itself, and then divided by this constant, negative c, like that. And again, evaluate this from 0 to x. So what we end up having over here, this equals 2, let's write this neater, x, and then this is e to the cx, put it underneath, and I'll show why later. So this goes to 0, and now we have this part right here, plus, plug in the x. So we have, this is going to be e to the negative cx over negative c, and then subtracted by, but there's already a negative, just put a plus, put in the 0, e to the 0, t is 0 times anything is 0, then negative, the negative's already there, we already canceled the negative here, so it's just divided by c. So we have that. I'll write this neater one more time. So again, this means that the integral from 0 to x of t c e negative ct dt is equal to negative x e to the cx plus, this one I'll put a negative like this because there's a negative sign like that, and again this e to the 0 goes to 1, so we have 1 over c. So now we have minus e to the, let's flip this around, so this is going to be 1 over c e to the c, just get rid of that sign. Yeah, plug in this cx, just get rid of the negative one, and then this will make more sense when we do the limit. Then plus finally 1 over c. So that's what this integral equals to. So when you go all the way back here, so now we take the limit as x approaches infinity. So thus mu, the average value or mean value, is equal to the limit as x approaches infinity of the integral from 0 to x t c e negative c dt, which is this whole thing right there. So this equals 2, and now let's plug this all together right here. Well, this is infinity. X goes to infinity and not 0. So this equals to the limit as x approaches infinity, and now we have 3 parts. Negative x over e to the cx then minus 1 over c cx, and then plus 1 over c. So what this equals to, what we end up getting here, if you plug in infinity on the top and bottom of this one, we get a infinity over infinity. So this is indefinite. We can't solve this one directly. We have to use L'Hopital's rule, and I'll get to that in a bit. But if we look at this one here, when we plug infinity, we get a 1 over infinity, which is again 1 divided by a really large number, it goes to 0. So this means this whole value is 0. Write it like that. And this one is a constant, as there's no x value, so that's just 1 over c. So this average value is going to be equal to, goes to a limit as x approaches infinity of negative x e to the cx, and then this one is 0, and then that's plus 1 over c. So you just take the limit out, plus 1 over c. So we just have to solve for this one right here. Yes, so now what you have to do is basically to solve that, recall L'Hopital's rule, and it's often spelled like hospital. L'Hopital's rule. And then this one here is basically limit as x approaches a of function if they're both differentiable, f of x and g of x, and then this equals to limit as, you could write this as the derivative of these, so limit x approaches a of the derivative of the top divided by the bottom. And again, this is if we have something like 0 over 0 in the limits, or infinity, or we can do plus or minus infinity over plus or minus infinity. Yeah, and also make sure to watch my earlier video on this. I'll put the video link below. You'll learn more about it, also more on the conditions of fx and g of x. So first, they just need to be able to take the derivative of them, and also the bottom here, as you get closer to whatever variable you're going to, you can't have g of x equaling 0 or near a, because then you'll have another invalid case. So again, make sure to watch my earlier video on that. But again, since this integral right here, this function e to the cx and x, there's values for it for any number, so it's not a problem. So what we have in our case, we have limit as x approaches to infinity. So our a is infinity of negative cx over e to the cx, like that. Now we take the derivative of this. So this equals to limit as x approaches infinity. Let's just put the negative x on top. So then we have the derivative negative 1, and the derivative of c, e to the cx, that's e to the cx, and then times by the constant using chain rule, c. So now when we plug in infinity now, because we take a derivative using L'Hopital's rule, we get, basically we have a case where this right here is a 1 over infinity, or a negative 1 over infinity, because x goes to infinity, e to the power of infinity goes to infinity. So again, 1 divided by a large number, that's a 0. So another way of thinking about why this is so is basically looking at this function x and e to this cx. This is just basically stating that the bottom part goes to infinity faster than the top part, so you're going to be approaching 0. Yeah, because it's a exponential function, so it exponentially goes to infinity faster than linearly going to infinity like that. So this goes to 0, so that's 0, and we could write this as 0. So this means, putting this all together, so that all together we have mu is equal to, well, everything else is 0, all we're left is 1 over c. So mu is equal to 1 over c. Yeah, and this is the average value, average mean value of that probability density function. But in fact, what we could do is, well, we could rewrite this. Let's write so if we rewrite this in terms of mu, so solve for c, so c is equal to 1 over mu, or over the mean. So when we do this, thus what we end up having is, if we look at the function, we have f of t is equal to interval like this equals 0. if, write it further out, if t is less than 0, but now we have c, e negative ct, but the c is equal to 1 over u, or mu. So let's write that over. 1 over mu, this is going to be t over mu. Let's write this a bit neater. Negative t over mu. If t is greater than or equal to 0, like that. Let's write this a bit neater. Okay. Yeah, so in other words, the constant value here for this probability density function is equal to the average value. Let's draw this a bit neater. Alright, so that's, yeah, neat enough. Anyways, all for today. If you learned from this pretty interesting video on determining the average value for this, again, this exponentially decreasing probability density function, and showing that the constant value c is basically the average value or the mean value. Anyways, that's all for today. If you learned from this video, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.